blocked by the errors between these two ways to deal with the age of the universe and its extension rate as estimation innovation turns out to be more exact, more modest varieties emerge driven by the improvement of further developed frameworks. This progress unexpectedly raises a greater number of inquiries instead of giving conclusive responses, albeit the contrasts are peripheral with simply 10 to 20 million years isolating the gauges, given that the universe is roughly 13.77 billion years of age. It still merits cautious examination. One conceivable clarification for this disparity is the chance of blemishes in our estimations of the CMB. Regardless of being one of the most exact estimations, it has been widely tried since its send-off in 2013 for approving its exactness. Another viewpoint proposes a potential hole in how we might interpret dim matter, raising the possibility that it might differ over the long haul and be connected with dull energy or some other obscure element. This chance has driven to various exploratory investigations. The precision of cosmic explosion estimations is additionally addressed, as the intricacy of star blasts can present vulnerability into the models we use. Settling this vulnerability in cosmic explosion models could help resolve the error in estimations. This emergency in cosmology has been additionally exacerbated by the revelation of the James Webb Space Telescope Accord. As per Neil deGrasse Tyson, the JWST tracked down objects in the universe that challenge our current understanding. This implies that our logical seeing necessitates a complete upgrade. However, the issue is that we have no clue about where to begin to grasp the greatness of this logical end of the world. We should take a gander at the starting points of the universe around 150 million years after the enormous detonation. Stars, dark openings and star bunches started to arise perhaps even as soon as 50 to 100 million years after the fact. Anyway, these occasions ought to be somewhat interesting. What we don't know is how normal cosmic systems advanced at later times, spreading over occasions among 200 and 400 million years after the enormous detonation. Ongoing JWST pictures uncover cosmic systems much more far off and in this manner more established than the standard cosmological model predicts. This inconsistency recommends that our model needs a huge update. The disclosure that the extending universe relied upon universes is an essential development. JWST pictures show worlds that framed significantly sooner than anticipated by current cosmological models, setting off an emergency in the field. This issue is connected with universes and red shift, which is a typical estimation in cosmology. As per the norm model, hydrogen started to seem 400,000 years after the huge explosion when protons, also electrons, consolidated, prompting hydrogen recombination. This changed the universe into a soup of hydrogen molecules with some helium and remaining foundation, the gravity of the radiation, then followed up on little irritations in this hydrogen gas, gradually imploding them to bring about the main stars. These early stars made essentially out of helium. Also, hydrogen partook in atomic combination, making heavier components, for example, carbon and nitrogen. These components assumed a basic part in cosmic system development by retaining warming and emanating cooling photons, which worked with the coalescence of gas into systems. The course of universe development. Also, development is perplexing and includes many stages, including the converging of more modest designs to shape bigger ones. Also, the continuous development of new stars from interstellar gas. Anyway, the JWST has noticed cosmic systems that framed a lot sooner than anticipated by our current models, proposing that we might have to change how we might interpret the early universe. This new information challenges our existing hypotheses and brings up issues about the cycles that prompted the development of the primary cosmic systems. The ramifications of these revelations are significant, as they could prompt a huge change in our comprehension of the universe and its beginnings, to further expand on the emergency in cosmology and the extraordinary effect of the James Webb Space Telescope. JWST. It is fundamental to investigate extra parts of our current understanding and how groundbreaking perceptions challenge this information. One critical area of continuous examination is the nature of dull matter and dim energy. While the lambda cold dull matter lambda CDM model integrates dull matter as a fundamental part that impacts the arrangement, the concept of dark matter, though vast in scope, remains elusive. It is thought to consist of particles that do not interact with electromagnetic forces, making them invisible and detectable only through their gravitational effects. Various candidate particles have been suggested, such as weakly interacting massive particles, WIMPs, and axions, but none have been definitively identified. Similarly, dark energy, which is responsible for the accelerated expansion of the universe, remains a profound mystery. Often described as a property of space itself or as an energy that permeates the universe, dark energy appears to drive the rate of cosmic expansion. Understanding its true nature could significantly alter our view of the universe's future. If dark energy is constant, the universe will continue expanding indefinitely, whereas if it fluctuates over time, it could lead to a more dynamic and complex cosmic future. The James Webb Space Telescope, JWST, offers unprecedented insight into these enigmatic components by peering deeper into the universe than ever before. By observing the formation of the earliest galaxies and stars, the JWST could provide crucial clues about the origins of dark matter and dark energy. For instance, studying the distribution of dark matter in the earliest galaxies may help identify the particles that comprise it. Observations of the rate of cosmic expansion in these early galaxies could reveal how dark energy behaved in the early universe. Another fascinating area influenced by JWST discoveries is the study of cosmic reionization. This event, which occurred between 400 million and 1 billion years after the Big Bang, marks a transition from a dark, opaque universe to a transparent one. During this period, the first stars and galaxies emitted intense ultraviolet radiation that ionized the surrounding hydrogen gas. Understanding this process is key to studying the formation and evolution of early galaxies, and it can provide insights into the universe's early conditions. The JWST's observations of high redshift galaxies, though so far away that their light has taken billions of years to reach us, offer a unique window into this early reionization phase. These observations could show how the first galaxies contributed to the ionization of the intergalactic medium and how their radiation affected the surrounding environment. If the JWST detects more complex and advanced galaxies at earlier times than expected, it could suggest that the process of galaxy formation and reionization was more rapid and intricate than previously thought. Moreover, JWST's capabilities extend beyond the early universe into the study of exoplanets and their atmospheres. By analyzing the composition of exoplanetary atmospheres, the JWST can search for signs of habitability or even biological markers. This includes detecting key atmospheric elements such as water vapor, carbon dioxide, and oxygen, which are essential for understanding the potential for life. The identification of such components in the atmospheres of exoplanets could offer vital clues about the conditions necessary for life and aid in the search for habitable planets beyond our solar system. In addition, the investigation of galaxy formation and evolution in light of JWST's observations challenges existing assumptions about the hierarchical growth of galaxies. Traditional models suggest that galaxies grow by merging with other galaxies and accumulating gas over time. However, if JWST data reveals that massive galaxies formed much earlier than expected, it could indicate that there were alternative processes at play or that our models of cosmic evolution are incomplete. This could prompt a re-evaluation of how galaxies assemble and evolve over cosmic timescales. Another challenge in cosmology is the need to reconcile observations across different wavelengths. The JWST, with its advanced infrared capabilities, provides data that complements observations from other telescopes like the Hubble Space Telescope, which primarily operates in optical and ultraviolet wavelengths. Combining data from these diverse sources is crucial for constructing a coherent picture of cosmic history. Discrepancies between different observational techniques may uncover new physics or highlight gaps in our current models. The interplay between observational data and theoretical models is a dynamic aspect of scientific progress, as new information from the JWST and other observatories forces theoretical models to adapt to account for new discoveries. This iterative process is a hallmark of scientific inquiry and illustrates how hypotheses evolve in response to observational evidence. In summary, the cosmological crisis, amplified by the groundbreaking observations of the James Webb Space Telescope, underscores the evolving nature of our understanding of the universe. The challenge lies not only in interpreting new data but also in integrating it into existing models or developing new frameworks that better explain observed anomalies. As our observational tools and theoretical approaches advance, we are gradually unraveling the major mysteries of dark matter, dark energy, galaxy formation, and the early universe. This ongoing exploration reflects the dynamic and self-correcting nature of science, where each new discovery leads to further questions and deeper insights into the cosmos. The differences in how we estimate the age of the universe and its rate of expansion have created challenges in cosmology. As estimation methods become more accurate, smaller variations emerge, driven by the development of more advanced systems. This progress raises more questions than answers. Although the differences in estimates are minor, just 10 to 20 million years apart, considering the universe's age is roughly 13.77 billion years, they still warrant careful examination. One potential explanation for this discrepancy could lie in imperfections in our measurements of the cosmic microwave background, CMB. Despite being one of the most precise measurements in cosmology, the CMB has been thoroughly tested since its launch in 2013 to validate its accuracy. Another possible explanation is a gap in our understanding of dark matter, suggesting that it might vary over time and possibly be connected to dark energy or some other unknown factor. This idea has led to numerous experimental investigations. The accuracy of supernova measurements is also in question, as the complexity of stellar explosions introduces uncertainty into the models used. Resolving this uncertainty could help clarify the discrepancies in measurements. This crisis in cosmology has been further intensified by discoveries made by the James Webb Space Telescope, JWST. According to Neil deGrasse Tyson, the JWST has identified objects in the universe that challenge our current understanding, implying that our scientific framework needs a complete overhaul. The issue, however, is that we don't yet know where to begin in grasping the magnitude of this paradigm shift. To understand the origins of the universe, we need to consider the first 150 million years after the Big Bang. Stars, black holes, and star clusters began to form, possibly as early as 50 to 100 million years after the Big Bang. These events were significant, but what remains unclear is how galaxies evolved during the later period of 200 to 400 million years after the Big Bang. The latest JWST images reveal galaxies that are much farther and older than current cosmological models predict. This discrepancy suggests that our understanding of cosmic evolution needs a major update. The discovery that the universe's expansion depended on galaxies is a pivotal development. JWST images have shown galaxies forming much earlier than expected by current models, triggering a crisis in the field. This issue is tied to the concept of redshift, a common measurement in cosmology. According to the Standard Model, hydrogen began to form 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This transformation turned the universe into a soup of hydrogen atoms, helium, and remaining background radiation. Gravity from the radiation then acted on small fluctuations in the hydrogen gas, gradually pulling them together to form the first stars. These early stars, made primarily of hydrogen and helium, engaged in nuclear fusion to create heavier elements like carbon and nitrogen. These elements played a crucial role in galaxy formation by absorbing, warming, and emitting cooling photons, which facilitated the clumping of gas into galaxies. The process of universe and galaxy evolution is complex and involves multiple stages, such as the merging of smaller structures to form larger ones and the continuous formation of new stars from interstellar gas. However, the JWST has observed galaxies forming much earlier than expected by current models, suggesting that our understanding of the early universe may need to be revised. These new findings challenge existing theories and raise important questions about the processes that led to the formation of the first galaxies. The implications of these discoveries are profound, as they could lead to a major shift in our understanding of the universe and its origins. To further explore the crisis in cosmology and the groundbreaking impact of the JWST, it is essential to examine other areas of our current knowledge and how new observations are challenging this information. One crucial area of ongoing research is the nature of dark matter and dark energy. While the lambda cold dark matter (lambda CDM) model incorporates dark matter as a key component that influences the formation and evolution of the universe, new data from the JWST may force us to reconsider our understanding of these elusive phenomena.